Welcome to Hidden Layers, where we explore the people and technology behind artificial intelligence. I'm your host, Ron Green. We're back today with another Decoded episode, where we take a look at important recent developments in AI. And as usual, we have a lot to cover. To help me make sense of everything, I'm joined by two of my fantastic colleagues. Well, my co-founder and distinguished engineer, ZZ Tsai, and our VP of Engineering, Michael Wharton. All right, Michael, ZZ, thanks for joining me.
Hey, thanks for having us.
Okay, I will kick us off as usual. I want to talk about the new release from Google DeepMind, AlphaFold 3. So this was a paper in Nature earlier this year where DeepMind released AlphaFold 3, which is obviously their third version of AlphaFold. As you know, I'm a really big computational biology person. This is another really giant leap in computational biology, even over AlphaFold 2. So AlphaFold is a model that was built by Google DeepMind to predict protein structure. So you can take amino acid sequences and predict what they will look like in the real world in 3 dimensions. Exactly. And this AlphaFold 2 solved. It's considered solved one of the grand biology challenges of predicting protein structure. In fact, it was such a success that Demis Hassabis and John Jumper, both from DeepMind, recently won, as you know, the Nobel Prize for Chemistry, right, for their work here. So what's really interesting about this and why I'm bringing it up now is just last week, DeepMind released the model weights and the model code. They open sourced it.
And it's truly open source this time, rather than.
So okay, that's a great question. I would
exactly
say
what I was going to ask.
Okay, so it's mostly open source, and I'll talk a little bit more about that in a minute. But the code and the weights are there. The big caveat is you can only use it for academic purposes. Okay, they're not allowing commercial use. But this is still, I think, a pretty
Absolutely, it's big progress. Right.
It really is. It really, really is. So a few things about this. Why is this so important? Well, proteins are like, you always hear they're the building blocks of life. They're involved in almost they're like the most essential molecules. And with our ability to predict these structures, these protein structures, we can use it for drug therapy, gene therapies, treatments for infectious diseases, all different kinds of things like that. And one of the things that makes AlphaFold 3 really amazing is that it supports not just proteins. Now, they've expanded it. It handles DNA, I'm looking at my notes, DNA, RNA, and other small molecules. So it's a much, much more broadly capable model. They said in their paper that it's capable of highly accurate predictions across different complexes, and those predictions are better than almost all of the dedicated models that are designed just to make predictions around one type of complex. So it can out-predict on DNA against all the other DNA models. Same thing with RNA, et cetera. They made some architectural changes that are pretty substantial as well. This thing called a paraformer, which I'm excited about, which is a diffusion-based model. So let's talk about that just for a smidge.
Yeah, could you go a little more detail about how that thing works?
Yeah, so this is what's fascinating. So it's basically got 2 parts to the model. There's something they call a paraformer. It's inspired by the transformer architecture, but it uses pairwise encodings for the entities. And the entities, if I understand this correctly, they've broadened it out. So the tokens that can come in can represent amino acids, and other types of molecules. So if they are dealing with structures that they've never seen before, they can encode that in a way that they couldn't before. And the paraformer, it's a deep learning architecture inspired by the transformer model, but it's designed to capture pairwise dependencies more effectively. And it uses self-attention, not only for the individual entity encodings, but also for the pairwise interactions. But this is where it gets cool. And this is why I think it's so exciting, is the the Performer makes predictions, and its outputs are the sort of the three-dimensional structures of the proteins or these other molecules, and then that goes into a diffusion model to refine it. Okay, right? It's pretty clever. And so let's talk about the diffusion model for a moment. The diffusion model, it says it represents the input, the protein structures in terms of atomic coordinates, residue interactions, and other structural features. And then they, using a normal diffusion approach, which let's just touch on that briefly. So the classic diffusion approach is you build a model to learn to remove some sort of known noise distribution, like some type of Gaussian noise distribution, and you progressively add that noise to some input, whether it's an image, and then you teach it to remove it and clean it up. Right. And they did the same thing here. They take in those atomic coordinates, and then they perturb them more and more and more with some sort of known distribution that the model can learn to unwind. And that's what they do here. So they'll take the pairwise or the Performer outputs and then refine it. And the beautiful part about this is that they said, let me look at my notes, they said that it can refine the predictions to handle complex folding scenarios, even in instances where it has never seen comparable structures, which novel
generalization.
Yeah, it's got great generalization. In the chemistry world, they call these homologous sequences. And so that means it's got much, much broader and stronger capabilities. Wow. So I'm really excited about that.
That is great.
It really is. And to come full circle, just to wrap this segment up, you were asking about whether it's truly open source. It's really not, because you can't use it for commercial, and they didn't necessarily release all of the training methodologies and stuff. But just this week, a new model from the MIT Jamil Clinic, they released a brand new competitor model called Bolt 1. And this is an AlphaFold 3 like model, both in design and capabilities, but it's released under an MIT license. So it is completely open source. I'm excited about this. They released both the training code and inference code, all the model weights, and the training data. And you can use this for commercial development. So I think that is going to be pretty transformative. And I don't know if this is the case, but I wouldn't be surprised if part of the reason that DeepMind went ahead and released everything was because they knew this was
imminent.
Exactly.
Could be, yeah.
Exactly.
That is amazing. I'm very curious to find out the scale of the training data and the training cost.
Yeah.
Given the great openness of the work.
Yeah, I'm right there with you. I'm very excited about it.
Yeah, it is really cool to see this kind of tug between the commercial world and the open source world. Like you see with the LLMs too, how it's kind of slipping back into that closed source territory. And then you have people like AI2 with Olmo and then Pythia that are like, not so fast. Let's just do this whole open kimono thing. And
I know.
It's really cool to see the push and pull.
I know. Keeping the dream alive of AI being, democratized.
Yeah.
I love it.
Yeah, I thought the pair transformer is very interesting kind of induction bias here. I know almost nothing about biology, but I'm curious whether this pairwise relationship is kind of inherent property in biological molecules.
I think that is the case. Yeah, I don't want to get out too far in speculation, but I think that is the case because you're dealing with every single atom or molecule is dealing with pair relationships with every other one of them, and so you can model those interactions. You can almost think about it as sort of like a graph structure. And I'm pretty sure that the Performer actually represents it in that way.
Okay.
Yeah.
Cool. Yeah, I wonder whether this also applies to other chemistry fields, other molecules.
Right. I would think so. I would think so. All right, ZZ, I'm going to go to you next. What do you have for us today?
I can talk about a little gossip here. I was watching the debate that came up, I think, every few months about the wall, like whether whether LLMs are hitting the wall.
The scaling wall. Can they get better with just more data or more parameters?
Yeah, exactly. So I think the two sides of the debates, at least what I observe is, on the one side there's Ilya who talk about, hey, the current scaling method is looking like it's plateauing, and Yang and Kun is also agreeing with that on Threads and then Twitter.
Yep.
Yeah. So on the other side, Sam Altman is saying, hey, there's no wall.
Yeah.
Yeah. So
well, what's interesting about that is, for Ilya to come out and say that, he was one of the biggest proponents of just let's see how far we can push the modeling with scale. And he's obviously left OpenAI. He's got his own company. And so there was a lot of speculation. We've talked about this on the podcast as well. Like, why was there such a brain drain at OpenAI? Why were so many people leaving if they were right on the cusp of having another breakthrough at ChatGPT 5 or something like that? And so it's looking like there are definitely some walls being hit on the scaling side.
Yeah. And I think interestingly, even for Ilya and Yang and Kun, who argue that, the current scaling methods are seeming to be hitting a wall, I don't feel like they're saying AI is hitting a wall. It's really, Yang and Kun never liked autoregressive LLMs.
No, he hated that.
Yeah, he has, his main idea right now, I think, is the energy-based model, the JPA thing. That's without the decoder.
Right.
So and Ilya, I think earlier hinted that, it's important at what dimension or at what aspect are you scaling. So maybe not the current scaling, but hey, there's this new scaling that I have that's gonna.
Oh, I haven't seen that. So Ilya's kind of been hinting that there's another dimension along which they might get scale improvement behaviors.
Right, and I think the current scaling law basically is the pre-training data and compute.
Yes.
And another thing that we already observe is from OpenAI, the O1, the test time compute, that's one dimension to scale. I wonder if Ilya is mentioning the same thing or some
other
totally new dimension to scale the data.
Yeah.
So is there, obviously there's this distinction between hitting a wall where data is the bottleneck versus algorithms being the bottleneck. Is that coming up in those discussions? I haven't really been on Twitter much.
I haven't seen it in this discussion yet, but yeah, I definitely feel like the architecture innovation, well, should we bet against it or should we bet for it?
That's big. If we're already training on the entirety of the internet, there's not a lot of juice left.
Yeah, for language data, I definitely feel like we're already using a lot of the language data, but image and video, I think we're still in the
we've barely touched.
Yeah.
Yeah, this is exactly right. Yeah, it's interesting times. I think, like you said, there are a lot of people out there who, interestingly, just kind of frustrated with the idea that it's not grounded maybe more deeply in science, and that the technique itself is so simple, and just throwing data and parameters at the problem feels maybe not clever enough to work. And they're shocked, kind of in hindsight, how long it did work. And now they're maybe happy that we're seeing those diminishing returns. I don't know. It's hard to predict where it's going to go. All right, Michael, what do you got for us?
All right. Well, sticking on the healthcare side of things, I saw this video the other day that I thought was just incredible. I think it was from this last week, and it was a video that Johns Hopkins released where they had this surgical tool. It basically looks like a couple robotic pincers. It's a tool called Da Vinci, and it's this platform that's been used by it's teleoperated by surgeons already. So they have tons
and what does that mean?
Like they literally are in a box outside of the OR, and they're controlling these two pincers almost like a video game.
Okay.
But it's still completely controlled by a surgeon who understands how to use these tools. And
gotcha.
Maybe it's like hard to reach places where fingers wouldn't be great, or like there are certain surgical applications where it's most applicable.
Okay.
But what they would do is, and that was like over 10 million surgeries that they have recorded like kinematic data for. So you can imagine that's a treasure trove of data.
That's much more than I would have expected.
Yeah, it's been. I don't think that when they put this platform in place, they were thinking, "Oh, this is going to be this data generation machine. It's going to be beautiful for machine learning problems later."
Side effect.
But yeah, I think they got lucky with this one. And what they did was, historically, it's tough to train robots to do things, and generalization in particular is really hard. But what they did was they employed this technique called imitation learning, where they had these kinematic trajectories of these robot pincers for various tasks. And then they trained a machine learning model to imitate that. And the way that they trained it ultimately allowed it to generalize a little bit. So I can get in a little bit of what they did technically on the architecture side. But I think it's really cool if you can go check out the videos of what they did. They had 3 different tasks that they trained this thing to do. One of them was tissue manipulation. So just, can you grab a piece of tissue and hold on to it? Another one was needle handling. It's like if there's a needle just sitting there, can you gently pick it up without damaging the tissue nearby? And then the third was actually knot tying, where it'll literally like have a piece of suture that just goes through actual tissue, and with these 2 little pincers, it'll tie a knot and tighten it in a gentle way.
That's crazy.
So check out the video because it's really, really impressive.
That is.
But what they did was a couple things. I think the choice of coordinate system turned out to be really, really important for them, because you can imagine, we know how important encoding is whenever you're trying to take a data set and make it available for machine learning algorithms. Like a GPS timestamp, you wouldn't just stuff that into a model.
Right.
Like if you can encode day of the week, week of the year, that kind of stuff, it's important. So it turned out the coordinate system where they're looking at the camera fixed coordinate system, where they have a borescope that's looking at the scene. That's what they used for part of the coordinate system. And then for the rotational elements, they used the actual rotation relative to the end effector for these robots. And those coordinate systems were used to directly encode these, you can call them kinematic trajectories. Does that make sense?
Okay.
I'm going off on a little bit.
No, this is great.
Does that make sense so far?
It does. You have more experiences with this than ZZ and me. So
Absolutely.
let me ask just a clarifying question. Yeah. So they had to figure out a way to encode all those 10 million recorded surgeries, and you're saying that the way they encoded the actual coordinate system played a big role. They think it played a big role in this success. Okay.
Yeah, that's exactly right. And they did show through ablations that is the case. They tried a bunch of different ones, and this specific, they called a hybrid approach, but that was the one that worked well. But what they do, here's diffusion kind of rearing its head again. Yep. They tried a couple of different techniques. One of them is called ACT, which is action chunking with transformers. And basically it's just, the architecture is nothing special. It's just an encoder decoder kind of, you have state data about where this robotic system is at a point in time. And then you have chunks of action sequences that you're training it to imitate from these old trajectories that they'd recorded from surgeries. And that worked reasonably well. And then they also had this diffusion model where they basically did something similar, but they conditioned the latent space on that particular type of action, like, tying a needle or tying a thread or something like that. But yeah, to just kind of tie it all into a bow, I think it's really impressive. And with a lot of these robotic tasks, it's kind of like evaluation metrics are kind of proxies for actual performance. It's either, did it do the thing or not? And there are a gajillion ways it could do that and still pass the test. But just go check out the videos. They're cool.
Let me ask you one question on the conditioning. When you say it was conditioned on the task, do you mean like they would describe what the task was and like had a learned embedding that it was conditioned on simultaneously?
Yes. And like a lot of these approaches, they'd throw the encoder away after they're done with the training, but they knew ahead of time that the particular modality that they were training on was either needle tying or tissue handling or whatever, and that's how they could instruct the robot later on what it would actually do.
See, I love this because if we can get these diffusion-based robotic models conditioned on a ton of different tasks, then you can just type what you want your robot to do.
That's exactly right. Yeah.
Yeah, and it will be successful.
Yeah, this is so cool. Thanks for sharing. I have so many questions. So what's the input besides the task conditioning? Is it the observation of the image, like, you know?
Yeah, that's a great question. So there are multiple cameras. I think there were 4 different ones. There's like a borescope that's actually looking at the scene. So maybe if it's like a laparoscopic surgery, it would be, you know, that's what's giving you the state of the whole scene.
Got it.
There were some cameras on the end of these 2 end effectors, and those were embedded and ultimately tokenized at this input for the encoder, as well as other state variables that you
got it, like the previous actions of the in actuators. Got it. And how do you represent the actions? You mentioned diffusion, so I'm guessing is it kind of similar to when you generate image where you have a VAE, variation autoencoder, to compress the action sequence. You mentioned chunking them. I'm imagining a long, like maybe 10-second action of sewing, and then you chunk it into, I don't know, half a second, or I'm just making numbers up. And then you compress that very complicated multidimensional action, like the actuator states, into kind of smaller, more compact embeddings as your tokens.
Did you read the paper?
No.
Yeah, that's pretty much it.
Oh, wow. Okay.
I think you got it.
It's amazing. It's amazing that, how the diffusion type of models can be applied to robotic, even long time horizon.
I know.
Yeah, it's really impressive. I just reading the abstract doesn't do it justice. I really would encourage everyone to just go check out the video and watch it.
Okay, we'll definitely put a video, or that video. We'll put the video as an overlay into the video version of this podcast for sure.
That sounds good.
That's awesome.
All right. So the next thing I want to talk about this new paper called Scaling Laws for Precision. We were talking about, scaling a second ago is easy. This is scaling in a different way. So this is a joint paper from groups at Harvard, Stanford, MIT, Databricks, and Carnegie Mellon. And what they did is they developed a precision-aware set of scaling laws. And so what that means is there are known, and we call them laws, but they're more like,
guidelines.
They're more like guidelines.
Thoughts to fit.
Yeah. So we roughly can predict, and have been able to, for, I would say 10 orders of magnitude going back a few decades, how models will improve based upon the increase in number of parameters and the increase in data. And, we were just talking about, are we at the end of that, right? Are we sort of seeing that this, what is probably like a sigmoid curve, start leveling out? Well, precision here refers to the number of bits that are being used to represent the floating point numbers for each parameter. So meaning, if I have a 1,000,000 parameter model, each of those parameters is a floating point number, and am I going to use 64 bits or 32 bits or whatever it may be? And they found that they could accurately predict the performance degradation of models, both pre and post training, based upon precision. So they were able to sort of unify the other scaling laws with precision. So 2 big findings came out of this. One, and the first one almost seems obvious, it's that training in lower precision, so if you were training at a 32-bit float and you went down to 16 or 8 or 4, training in a lower precision reduces the model's effective parameter count. You can keep the parameter count the same, but if you reduce the precision of those parameters, you're effectively and predictably, and that's the important thing, reducing the parameter count of the model. And the second finding is not intuitive to me at all. It's that they found that there was degradation introduced in post-training models that were quantized, and that degradation increased as those quantized models were pre-trained on more data. So it's a little hard to grasp. Let me say it again. So the more you trained a model, the more data you trained a model on, the worse its degradation as you quantized it. So you basically got diminishing returns. It became actively harmful to train on more data. And so The big takeaway from this is a couple of things. One is it's unifying these scaling laws for both post and pre-training quantization. And they arrived at a single functional form that can predict degradation from training and inference across various precisions. And I think probably most interesting is they found that it is probably compute optimal to train these large models at 7 or 8 bits, meaning we are probably over provisioning these models even at 16-bit. That's probably suboptimal.
That's good news for OpenAI's cloud bill.
It's really good news. It's really, really good news.
Yeah. I wonder what are the implications. It's with this new kind of dimension of scaling law.
My guess is that if 7 or 8 bits is optimal, that's great news across the board because it means memory, power, costs will go down, inference, latency, and costs will go down. And I've got a theory about this. This is just kind of a wild theory I'm going to throw out, but it's kind of tied to some things we've talked about recently, which is this idea of superposition theory, where knowledge or information or understanding within these large models is actually encoded using sort of nearly orthogonal vectors, right? And that allows this sort of superposition, almost like quantum theory superposition, for this information to be overlaid together across all these neurons. It's not like individual neurons are storing things. And I think the work coming out of Anthropic this year around interpretability points really strongly in this direction. So my pet theory is that for you to be able to have these sort of nearly orthogonal vectors, there is some minimum level of precision beyond which it can't differentiate. They become essentially orthogonal, or too far from orthogonal in actuality for it to maintain its knowledge. And it's that fine line of precision that we may be wasting bits on if we go above 7 or 8, or that we are harming ourselves if we go below. It's just my theory. So I don't.
Oh, that's super interesting, and I think it makes a lot of sense. There seems to be there may be a theoretical bound or limit as to how low bits you can get within each neuron in order to represent sufficient information.
Exactly. Totally agree. All right, Zizi, I'm going to throw it to you. What do you got for your second item?
Very related to your topic, Ron, about the scaling law. I'm personally very interested in learning, efficient model training methods, especially for pre-training. And on that, I've, two things, and I can talk about one and pass it over to Michael and then get back to my other topic. So one is the recent paper from Apple, and again, this Apple doing open source again. It's a method called CCE. I think it's called the cut cross entropy, which is a kind of a recipe to reduce the memory consumption during training, especially targeting the softmax layer. So the paper mentioned an interesting observation that for the large models, especially for models with a large vocabularies, all those large language models, the last layer is the softmax to predict the next token. And the softmax can take up a lot of memory, a lot of GPU.
And maybe just really quickly to flesh that out so everybody can have an image in their mind, you have to have an output node for every different token you want to predict, right? And so the bigger your vocabulary, the more of those output nodes, right? And it gets really, really expensive. You can have vocabularies that are 30,000, 50,000 up, and you have to have an output neuron for every one of those possibilities.
Yeah, exactly. So like when we're using ChatGPT, we're seeing word by word, but actually what happens is that, each word, there's a very, very long vector to lay out all the possibilities of the next word, and which can be, depending on the model, it could be a few 100,000, for the Gamma 2 models, for example. And those take up a lot of GPU memory. So this paper proposed a pretty kind of low level, like CUDA level, CUDA kernel level optimization to do two parts of the softmax loss computation. One is with the index matrix multiplication, and the other is dealing with the log sum exponential. And I read the paper a little bit. I think I only understand 20-30% of it. And it's a pretty clever trick that they use, which basically uses a different type of memory called SRAM. I think it's called the static RAM. So using that to carry out a lot of the computation instead of using the DRAM in a GPU. So in that way, they can reduce. Let me read the quote here. They reduces the memory footprint of the softmax loss computation from 24 gigabytes in GPU memory to 1 megabyte.
That sounds unbelievable. Is that real?
That sounds impossible.
It sounds almost too good to be true. But yeah, I'm definitely interested to try it out on some of the training experiments. But yeah, this is
that's really interesting. It reminds me of the Mamba architecture, which on paper, if you look at it, it doesn't have any of the sort of really significant computational gains that you would expect. But they reformulated a lot of the recurrent designs of it and were able to make it non-recurrent, and then also took advantage of specific hardware capabilities like differentiating between SRAM and DRAM. And that's where most of its computational gains come from. It's not necessarily just implicit in the formalization.
Interesting.
And this sounds like the same thing in a way.
Wow. Hardware level optimization.
Exactly.
Yeah. In a way.
Exactly.
And just a quick color here, and just to put it in perspective, along this line, I think there are some recent work that they compare with. There's the torch.compile. That's one way to make the training faster. There's the torch tune. I think it's released by Meta. And then Liger kernels. Those are the kind of the competing methods to make your training more efficient. And then there's the CCE that kind of competes in some aspects, especially the memory. So yeah.
Love it. Lots of great progress.
Yeah, that's amazing. Love hearing it.
I love
Michael, any news?
This is breaking with the computational efficiency train here, but I think this is still pretty interesting. So there's this paper recently that proposed this concept called HTML RAG, and it is very simple. I mean, it's not
super interesting,
not anything crazy or revolutionary, I don't think. But their whole argument here is that we should prefer HTML in that format as our structured knowledge base at rest format. Okay. Because right now, most of what we do, especially with LLMs, typical training corpora, we're just throwing away a ton of structural information and then just trying to represent it as plain text. I mean, anybody that's taken a PDF and just converted it to plain text has seen this. You get tables that turn into gibberish. You get a lot of stuff that's really unintelligible. But when you peek under the hood, that's really what's going on with all these plain text data sets. And you have things up to 15 trillion plus tokens that have all had this lossy pre-processing step happen to them. So there's an obvious downside to doing this. There's a token ballooning effect, just because there's a ton of extra, maybe under the hood you've got a bunch of HTML tags that are useless, or maybe you have some extra precision on digits that are represented that don't matter, whatever might fall into that kind of bucket. But so they had this data engineering scheme that they outline in the paper that's pretty straightforward. But what they would do is take out a bunch of redundant tokens that they don't need, like style tokens. And then they would try to encode this as a block tree. So they were trying to basically come up with the most efficient representation of raw HTML that still encodes the structure that was present in the data at rest, but doesn't waste too much on the token budget. It's kind of like a trade-off.
Like a pre-processing formatter?
Yeah, that's exactly it.
Huh. Do they have a different tokenizer, maybe?
Yeah. Wow. Yep, that's exactly right. So what they do here is test it against a bunch of QA benchmarks, because RAG systems ultimately like a QA task. And overall, using Llama 3.1, 8B, and 70B, the performance improvements are minimal, but it's still on the order of like 1% or so. And I'd say we're already kind of in, at least with existing models, we're in this land of marginal returns without any major algorithmic upgrades. So to have a pretty across the board slight improvement on some of these QA benchmarks, I think it's at least worth paying attention to. So.
Yeah, absolutely.
Yeah, it's a very practical AI technique.
Yeah, super simple, nothing too crazy complex about it. But if you're building RAG systems, I think it's something you should be very familiar with.
Yeah, very practical recipe, and I think it makes a lot of sense. So like, it's kind of like handing to AI instead of a plain kind of text. I will use a highlighter to color code it, and then write some notes, and then that would definitely help.
Right. Yeah, I think the intuition test that to me is like, oh yeah, this makes total sense. Is that it's just tables. Like there are tables that are formatted in HTML that are very structured, and then when you throw away all those tags, you're just removing very important hierarchical
That's exactly where my mind went, which is even if it's just the table information, you're probably going to see a boost.
Yeah.
That's great.
Well, yeah, Zizi, what's your last topic?
So before that, I'm really interested in the in your mentioning that the method is very good at parsing tables. I want to mention that I just had a quick chat with Jerry Liu, the author of Llama Index. He mentioned Llama Parse as a kind of a new development of Llama Index that is very good at parsing tables. I'm super interested in trying that out and trying the paper that you mentioned out to compare.
Yeah, I'd love to see how that works. I'm not familiar with it, but it sounds pretty cool.
Cool. And so what I got next, it would be about gaming. So I've been reading a lot about how Gen AI can be used for different industries, and gaming came out as one interesting vertical. So there's I think this new startup that came out with a game called Oasis. It's a purely AI generated Minecraft game. So
I heard about this. Yes.
And they have a link to play it. I tried it, but I think it's getting too popular now. When I go there, I got to the queue, and my position is number 164. but anyways, I think it's super cool because Minecraft, in order to make a game like that, don't you have to have a representation of meshes, textures, and the ray tracing, etc. But I think what this new Oasis game does is that they purely rely on AI to generate pixel by pixel using the diffusion models without any representation of meshes. At least that's what I understand it to be. There are still a lot of glitches. I think Michael, you also played with it. Like sometimes there are graphs suddenly pop up, and when different kinds of inconsistencies. But I just thought it's super cool and wanted to share.
Yeah, that was exactly what my experiences were. It was, you can tell the world model is really kind of transient, because if you're navigating the player in the game and then you do a 360, you come back to your original spot, it's a completely different world. Totally, it's not consistent. Or if you look off in the distance and you see something really far away that you want to go check out, just by walking toward it, that feature, whatever it is, just naturally changes and disappears. But it's kind of trippy. I think it's really interesting. But
I think it's fascinating. It clearly has a very soft world model.
Yeah.
But I love the fact that you pointed out, Zizi, which is, the ray tracing and the light diffusion and all of those other things that are typically built into these physics, game engines. All of that just is emergent. It just kind of appears here without being explicitly coded. I love it.
Yeah, I can't wait to see what happens in the game industry in the coming years. Actually, my next topic is kind of related, but there's so much, it's ripe for innovation.
Okay, well, Michael, why don't you wrap us up today with your last topic?
Yeah. Cool, that sounds good. Well, there's a new architecture that came from NVIDIA, their research team in Toronto, and it's called LlamaMesh. And really what they're trying to do is take a pre-trained Llama 3.1 model and use all that it has just from looking at its own training corpus, and do a little bit of supervised fine-tuning with some meshes that were defined in a pretty standard format.
And when you say meshes, you mean computer graphic? meshes?
Yeah, like a mesh of objects like a lamp or a chair or just things they happen to have in their training data set.
Okay, gotcha.
And just with a little bit of supervised fine tuning, they were showing that, you can generate these really impressive meshes. You just ask for, a lamp or a chair or whatever. But at the same time, they measured how much performance degradation they had against common benchmarks. And it was still it was like 5% on the MMLU benchmark. But the fact that it could be able to do that and succeed at it, I would say, and still have slight hits and still have, some sort of conversational ability. I mean, I thought it was really impressive to check it out. And
yeah, that's crazy. How do you use language model to generate meshes? Like what?
So what they do is there's an issue about tokenization, obviously.
Mm-hmm.
And what they did with their training data set is they came up with this standard way of tokenizing meshes. So they have, this standard coordinate system that they convert other meshes to if necessary, so that they could represent all of the coordinates with integers and do it in a compact representation. Because you can imagine, like, if you have an x coordinate of 2.33333333, that's a lot harder for a language model to understand instead of just sequential integers that are a little bit more straightforward.
Right.
And in using this fine-tuning data set they used, I think it was about 2,400 GPU hours, which is a decent chunk. But when you compare that to 1.5 million to train your typical llama model, I think it's pretty training efficient too for something like that.
Wow, amazing. Yeah, I think, the multi-model generative models are really secretly more efficient to train than language models, I feel.
I think that's exactly right.
Oh,
especially when you have a small data set that's really descriptive of a task that you want to fine tune it to. It's a lot more efficient.
Oh, that's super cool. And then, it's funny. Last point, they have to. What was it? LlamaMesh.
Mm-hmm.
I love that because
that's right.
Right.
Yeah.
Meta's new licensing rules require you to use the word llama in any derivative works. We're going to see a lot of more llama stuff.
Yeah, I think you're right.
All right, guys, this is awesome. ZZ, Michael, thank you both as usual. This was a blast.
It's so fun.
Yeah, thanks for having us.
Thank you for listening to Hidden Layers. This series is hosted by KUNGFU.AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at KUNGFU.AI.